Cool. Welcome. Hopefully everybody had a good lunch. Thanks for coming to my talk. I'm Michael Bailey. I'm an engineering director at American Express, an Android developer. We've got a lot of American Express people here. I think there's like 9 of our Android devs here today, so stop by our table, ask questions after the talk if you don't get a chance to ask during the talk. Today I'm talking about how the MainThread works. So what is the MainThread? So on Android, there's a concept. It's a Java thread. So just like any other Java that's not on Android, it's a thread. But it's a specific thread that's started by the system, and that's what we're going to talk about today. It's where the UI does its drawing. It's where your view code gets drawn. It's where other UI callbacks will get called. There's one main thread per process. Most apps are one process, but if you split your app into multiple processes for services or other things like that, you can have one main thread per process. And also, a lot of times, you'll see it called the UI thread. It's the same thing. Main thread, UI thread, same thing. And I'll note there are a few exceptions to when things are called on the main thread from the system calls, and those are usually called out in the Android docs, sometimes related to iBinder or content provider or other things. So just make sure that you check the docs if you're assuming that something's being called from the main thread. So just a brief history, what is a thread? It's a main thread, but what is a thread? So we're talking about a Java thread here. It's not part of the runtime definition per se, it's part of the actual language. A thread is kind of a first-class citizen. The Java language spec has a whole chapter that defines exactly how threads work, how things can be transferred from one thread to another, how synchronization works in a lot of detail. This is an actual quote from the Java language spec. It says, "The behavior of threads, particularly when not correctly synchronized, can be confusing and counterintuitive." That's probably an understatement. If you read through there, it's a little bit dense to go through, but it does have some unexpected behaviors. The good thing is it's very well defined. There's a memory model that tells you exactly how things are going to work and how a compatible implementation of the Java language, what they are allowed to do in terms of cross-thread and how synchronization has to work. So this is one thing I wanted to call out. This book is great if you really want to understand how threads work. And in most Android apps, you are having more than one thread. And if you're having more than one thread, you really want to understand how they work, how synchronization works. I'm going to give one example out of this book just to motivate the case that you should read this book, just to understand. I always say if you read this book, you'll realize that all the multi-threading code you've written before you read this book was probably wrong. And here's a simple example from the book that just motivates the point that threads can be a little bit unintuitive at times. So if you look here, we have an example of code that I took from the thing. So there's 2 threads here. I'll go back here. The main thread, the main method starts a thread, and then it assigns a number to 42 and assigns this to ready. Then this other thread goes off, and it just polls and spins while ready is not true. Of course, it's going to be true set down here. And then eventually, if ready is true, it will get down to this print, and it will print the number. So does anybody know what are the possible things that a correct Java language implementation could do in this case? So there's a couple things it could do. One thing it could do is just print 42. Ready is true, goes through the loop, it prints 42. Another thing it could do is it could spin forever. Because there's no synchronization here, there's no guarantee that this other reader thread will ever see the value that's set to ready, because there's no synchronization. And this book explains all the details of how to work around these types of things and how to do it correctly. The third thing that a correct implementation could do is it could actually print 0, which to me is at least the least intuitive thing that could happen here. Because number is set to 42 before ready is set to true. So you would think that if it exits that while loop and ready is true, then number would be 42. But that's not guaranteed to be the case. Without proper synchronization, Java can actually flip the order of operations from the view of another thread. On that thread, operations will always happen in source order. But from the viewpoint of another thread, without proper synchronization, things can actually be flipped. So a compiler could do an optimization and basically flip the ready equals true before the number equal 42, and you would print the default value, which is 0 there. So there's a lot of great things in the book that tell you how to do it right, and it doesn't have to be so mysterious and painful. So now that we've kind of talked about threading and that it can be mysterious, we're going to get more into the main thread in Android. So let me explain to you how the main thread works. So in Android, there's a Zygote process that lives on the system, and when you start a new process, you basically get a kind of a copy on write type copy of that process, and then they will invoke this thing that's in the Android. They will invoke a main method, public static void main, inside of a class called activity thread in your process. And this is where it all starts. Inside of there, well, one main thing that happens first is it prepares the main looper. This basically installs a looper into the current thread. And then it calls Looper.loop. And this will never exit. You can see it throws a runtime exception if this ever exits, because this just is the main event loop. In a lot of UI kits, there's always a run loop or an event loop or something that's processing. In Android, it's based on the looper. Now, any thread in Android could have a looper. The main thread always has a looper. And it's a very specific looper that you can get a handle on, and we'll talk about that in a bit. So then the question is, what's a looper? So according to the docs, it's a class that is used to run a message loop for a thread. So every thread has 0 or 1 loopers. By default, there's 0 loopers. If you call looper.prepare, that installs a looper into the thread that was called on. The looper is not running until you call looper.loop. And that starts the processing of this event loop or message loop. So let's look at some of the code. This is a lot of these code samples have been edited to fit on a slide, and I threw out some of the stuff that wasn't quite as important to what I was talking about. But these are from the API 22 source, just to give you an idea of what it's doing. So when you call looper.loop, it calls myLooper. So myLooper looks at the looper that has been installed on that thread when you called looper.prepare. Then it goes into that looper and gets a message queue. So every looper has a message queue, and we'll talk about message queue in a moment. Then it goes into the message that it got out of that queue, and it goes queue.next to get the next message, and then it dispatches that message. And you can see this is all contained within an infinite loop, for semicolon, semicolon. So we'll do this over and over again. It will get the next message. It will call dispatch message. Next message, dispatch message. And that's the entire lifetime of your app. The main thread is doing this. So what's a message queue? If you look at the message queue API, there's like almost nothing there. Nothing very useful anyway. In 23, they added some methods regarding file descriptor. I'm not going to get into that today. But other than that, there's methods to add an idle handler and remove an idle handler, which is not. This is the main message queue. You can get the message queue from the looper, but you can't really do much directly with the message queue. Internally on the message queue, which is not a public API, and really this is just more for information when you're debugging and things like that to know how it's working, it's a queue of messages. Inside, it's a linked list of messages. And they're processed at a given time. So the next, when you call next on the message queue, which is not a public API, it gets a message off the front of the queue, and then it dispatches that message, which means it's getting processed. Messages have a time, which is the earliest time that they're allowed to be processed. So if there's no messages that have yet meet their time when they can be processed, then that next call will just block, and it'll just wait until somebody gets to the front of the queue at the time that they can be processed. The important thing to note is that the timing on the main queue and the main thread is all based on system clock.uptime millis. Now, the interesting thing about this call is this is the CPU clock. which means that if the CPU goes into deep sleep, this clock gets paused. So anything you put on the main thread, you say, put it out there 5 seconds in the future. If the CPU goes to sleep, which means there's no alarms waking up, the screen's off, it's not plugged into power, these conditions generally lead the CPU to go into the deep sleep mode, that clock gets paused. So if it's paused for 3 seconds and then it wakes up, no time has passed, and you said for 5 seconds in the future, so it might not actually get to the front of the queue for 8 seconds, depending on when the CPU is asleep. So putting things on a queue and expecting them to happen at a certain time, you have to remember that this CPU sleeping comes into effect. All right, so I talked about messages. So what's a message? It's a class in Java. It has a when. A when is that time that I was talking about. It's the earliest time that it can be processed. Depending on what's going on in the queue, it may be processed after that time if other things are before it, because these messages get processed one at a time on the made through. We saw that for loop. And when it becomes the turn to dispatch that message, if the message has a callback, which is a runnable, then it will call run on that. And that's how that message is processed, by calling run on the runnable. If there's no runnable on that message, then it looks inside the message and it gets a target. The target is the handler that I haven't talked about yet, and I'll talk about in a minute, that the message was created with, and it will call handle message on the handler associated with that message. I should also note that messages are part of a global pool of objects. So you get a message by calling obtain. You don't new it up. And when you're done with it, you have to call release. And again, most of this is just internals of the main thread. But the point is, knowing all this stuff can help you better debug things when you're having problems and things like that. So MessageQueue really doesn't have an API. So how do you get message added to the MessageQueue to add them to be processed in the future? That's where handler comes in. And handler is kind of a weird name for this class because it really does two things. It adds messages to the message queue of the looper that it's associated with. And then it also handles messages when those messages don't have a callback. So when you call one of these post messages, it will add a message to the message queue. You can call post. When you call post with a message, it adds it to the end of the current line of messages that are currently eligible to be processed, meaning their time has passed and all the things they're ready to be processed lined up. So it gets in the back of the line of all the stuff, in front of all the stuff that's going to be processed in the future, but behind the stuff that's ready to be processed now. Post delayed sets the when time to some time relative to now. And the difference between post delayed and post at a time is one is relative, like 5 seconds from now, and one is more an absolute time based on uptime millis. But that puts it, the when in the future so that it's not eligible to be processed right now until that time passes. Then there's post at front of queue, which is an interesting thing. If you think about this, you're putting something at the very beginning of the message thread. So you're jumping in the very front of line. So if you have these all over your code, people at the messages at the back of the line will never make it to the front. So if you have it one time in your code, then maybe it could be you could reason about it and sort of understand how it works. But if you have different parts of your code, putting things at the front of the message queue, it's going to be very hard to reason about what is going to get processed or if something will ever get processed, because it might never get to the front of the queue because everybody's jumping the line. And there's some great blog posts that I have mentioned at the end of the talk by PY that talk about the main thread and go into some of this stuff. And he recommends don't using this. I think that's probably good advice. The other thing that the handler does is if you didn't provide a runnable or a callback, it will just hand you the message and say, handle message. And it will hand that to your handler. So you can create a handler like this. And to me, this is one of the things that always is a little confusing when I see this, because you have to think, like, what looper in MessageQueue is this handler attached to? It's just a new handler. Anybody know which MessageQueue or loop this would be attached to? Yeah. So, well, the thread that this was executed on. So whatever thread the handler is executed on will be, if it has a looper, meaning looper.prepare was called, it will be attached to that looper. Otherwise, it'll throw an exception if there's no looper currently attached to that thread. which is a little bit mysterious. So there's two other ways of calling it. One, if you always want to get a handler to the main thread, you can call looper.getMainLooper, which is that special looper that's created in the activity thread at the very beginning of your process. And you can get a handler so you can post messages into that thing. The second one essentially does the same thing that that last one did with no parameters to the constructor. But in this case, it's more explicit. Like, I am getting my looper and I'm getting a handler to it rather than just this constructor that's like, you have to remember, oh yeah, if I don't pass anything in, it gets the current thread. I find it a little bit more clear. So this is the basic structure of the mechanics of the main thread. As an example of something that uses the main thread, there's a thing called Choreographer. And this is responsible for basically getting frames displayed and pushing the UI code, putting the messages on there so the UI code gets pushed to the GPU and ultimately on the screen. So it has a frame handler. It's just an instance of the handler. It gets a message. It uses obtain message to get one out of the pool with a specific, if you look over there, it says message.what. That's just an integer that you can put in there so you know how to handle that message. It says set asynchronous, which if I have time, I have a slide on kind of talking about that a little bit at the end. And then it sends the message at the time. So this message doesn't have a callback. And so eventually, when it gets to the front of the queue and can be processed, it will go into handle message. And then it has a case statement to handle it appropriately. So this is how Choreographer works. And this is the one that's drawing that frame every 16 milliseconds on your main thread and forcing that to be drawn. So that's why you don't want to hold up, one of the reasons you don't want to hold up the main thread is because this guy's going to draw whatever the view hierarchy is at that moment. So if you delay the rendering of your view or the updating of your view by too much, then it's going to skip all the way to the next frame gets drawn on that specific time sync, because you can see it sets the message at the next time frame. So just because you were 1 millisecond late, it's not going to draw the next frame till the next 32 milliseconds or whatever it is. So just missing that frame cutoff by a little bit actually can, it skips to the whole next time that this gets processed. Just a brief note that on API 21+, there's a thing called RenderThread. You pretty much never really need to know about this. It's a way for them to offload some of the code that pushes the UI to the GPU onto a non-main thread. It opens up some throughput because it's doing a little bit less every time that it does that, because it can do it on a background thread. Something to know about. You still should be careful on the main thread, even though this opens up a little bit more room on the main thread. So what are some implications of how the main thread works? If something takes too long on the main thread, then other things aren't going to be able to get to the front of the line. They're not going to be able to be processed. So you can drop frames, like I said. If you put too much stuff in there and your views can't get drawn, and your view hierarchy can't get built and drawn and laid out in the right amount of time, then it's going to drop frames. Essentially, it's going to nothing is going to be updated by the next time it draws that frame on that every 16 milliseconds. Events get processed on the main thread. So when you touch the screen, that ends up as an event on the main thread. So that is going to have to wait till it gets to the front of the queue to get processed. And if you really delay the main queue, you're going to get an application not responding. If something takes roughly 5 seconds, I guess, on the main queue, probably depending on the Android version. So the Android thread rules. This is actually from the Android docs. They say there's 2 simple rules. Don't block the main UI thread. So let the messages that you put on there should be processed very quickly. And don't access the UI toolkit from outside the UI thread, meaning you shouldn't call into views from outside the UI toolkit. Now, interestingly, I saw a talk yesterday from the Facebook guys about how they're doing screenshotting. And their solution is essentially inflate things on the instrumentation thread and then render them on the instrumentation thread and send them to a file, which violates this rule. And if you look at the view code, it actually works because the view code does, in certain paths, check what thread it's operating on and will throw exceptions if you try to call things on the wrong thread. But it actually, what it does is checks that you are operating on the view from the same thread that created the view. So if you inflate your view on the instrumentation thread and then you operate on it, you're operating on the same thread, so it's not going to throw those exceptions. And apparently it works because they're going to open source that library, which is could be useful. So things that you shouldn't run on the main thread. Really, the criteria is anything that you don't know takes a very short amount of time. If it's variable amount of time, sometimes it's fast, sometimes it's not. You don't really know. You probably shouldn't run it on the main thread. Things like network, obviously. Disk reads can be fast, maybe, if the disk on the phone happens to be fast, but you don't know. So it's not a good thing to do on the main thread because there's no performance guarantees around that. So things that you're executing on the main thread should be very short and predictable amount of time. So then how do you run stuff not on the main thread if you're not supposed to run it on the main thread? There's a couple different ways. Not all of them are listed here. But a few of them are, there's stuff in Java util concurrent that's just Java stuff, not specific to Android. There's executors and various concurrency mechanisms in there. The good thing about that is they have good primitives, but they're not Android dependencies, so you can use them in a non-Android project, and you're not depending on Android. They're pretty simple, and a lot of times you want more coordination, more control over what is given to you there. So it's a pretty plain layer for trying to put stuff on a background thread, but you can use that. There's async task. One of the downsides of async task is it is a Java class or a Android class. So if you're using the one built into the platform, then it makes it harder to test with just plain Java unit tests. It's also, if you're doing, it basically just splits things up into run this thing in the background and then process this result on the main thread, which is fine if you're doing that simple thing, but if you want to coordinate multiple things, it becomes pretty difficult. There's not great error handling with that. Another good thing about async task is it does come with Espresso support out of the box, so Espresso will wait for your async task to finish before it operates on your UI. But you can accomplish that with these other mechanisms through things like idling resource with Espresso. So I personally don't use async tasks, but I use RxJava. We use RxJava in our app. The downsides of RxJava, it can be pretty hard to learn and wrap your head around. It can be hard to debug when things don't happen the way you thought they were going to happen. Debugging through like what's going on, how do I fix this, can be a little bit of a mixture with RxJava. The good thing about RxJava is it gives you some ways to, it definitely is great for coordinating multiple things going on. It has a great model for that, and it has kind of a pluggable concurrency model. There's a thing called scheduler, so you can, independent of what you're doing, you can kind of manage when and where things happen on certain threads. So I think it's probably, I mean, it's worth the learning curve. But initially, you can experience some pain trying to wrap your head around it. Another thing I should note when you're trying to understand what's happening on your main thread and are you doing anything that you shouldn't be doing on your main thread, there's a thing called StrictMode that you can turn on. There's two parts of StrictMode. There's a thread policy where you could say, these things aren't always bad, but on this thread, they are bad. So like disk reads aren't bad on all threads. Sometimes you need to do disk reads, but on the main thread, they're bad. So from the main thread, you can set a thread policy that says, detect when I do a disk read from this thread, and then you can say the penalty, just log it, or crash the app, which if you put penalty death, then it'll crash your app when you do the wrong thing. Then there's also VM level policies, which are things that you'd never want to happen no matter what thread you're on, and they're just VM wide. Things like leaking SQLite objects and things like that that you want it to detect and tell you about. So I've talked about the main thread. There's one other important thread that, especially if you're doing testing, that you definitely want to know about, that is not the main thread, and that's the instrumentation thread, or sometimes called the test thread. So instrumentation is the top-level class of your instrumentation test runner. So if you have an Android JUnit 4 runner, or if you have your own custom implementation class, the grandparent of all that is the instrumentation. And inside of there, when you call start, before it runs any of your tests and goes through the normal test runner stuff, it starts this new instrumentation thread, or it creates it and calls start. So all of your code inside your tests, when it runs, is running on this instrumentation thread that is started there. So what is that? What are the implications of that? Well, this would be bad. Here you're launching an activity, but then you're just going right in and you're finding view by ID and you're manipulating views, but you're not on the main thread. There's a couple things that can go wrong here. One, you don't know the state of the main thread, like what's going on over there on the main thread, because I'm on the instrumentation thread. Is the view hierarchy built? What's the state of the activity? You're also calling into view methods from a different thread than the views were created on, so in certain paths you'll get exceptions. There's also, like I showed at the beginning, there's cross-thread visibility, so you might not even be, depending on the synchronization, views aren't meant to be used on more than one thread, so you may not be seeing the right state of the views and things like that without proper synchronization. So this is just going to cause you problems on multiple levels. So what should you do instead? Well, there's Espresso. So this is what a test may look like using Espresso. This test is still going to be run on the instrumentation thread, but underneath the covers, Espresso does all the things that you need to do to make this not flaky. So here, it's getting a view with a certain ID, and it's performing a click on it. Looking at the view has to happen on the main thread. Performing the click has to happen on the main thread. But here, it reads nicely, and you don't have to worry too much about that coordination between the main thread and the instrumentation thread. So Espresso does a lot of things, but two of the things that it can do for you, it makes sure the UI things happen on the UI thread. In that last code, you didn't really have to worry about the UI thread, but Espresso underneath was making sure that the UI things happen on the UI thread. And it manually, for lack of a better term, progresses the main thread message by message, checking for certain conditions so that it knows exactly the state of the main thread and of your whole UI, so that when it operates on something, it knows that, OK, now's the right time, the right things have happened on the main thread. So you don't have this sort of guess like what's going on in the main thread. Espresso does that coordination for you. So here, at the beginning, we saw a method called loop. This is from Espresso. So Espresso has this thing inside of it called loop until. And if you notice, there's a similar structure here to what we saw in loop. This is actually going to be executed on the main thread. So you're already inside the looper. You're already processing a message. But inside of that, Espresso is actually reflectively going into the message queue, grabbing the next message, and calling dispatch message on it. And then it goes in this while loop and checks, are the conditions I'm looking for ready yet? Otherwise, go and process the next message, and go and process the next message. So it gets into your main queue, and then it reaches forward for the next messages on the queue, and then it processes them one at a time until the conditions are ready for the next thing to happen in your instrumentation tests. And it's great that Espresso does all this for you so that you can write UI tests in a simpler way and not have to worry about this. So when you're going through your code and you're trying to understand, wrap your head around what thread is running on what, because you can have other threads that things run on. If you're running Picasso, it can create threads in the other frameworks. So it can all get a little bit much to wrap your head around. If you set a breakpoint on a line, you're like, where is this running? Why am I seeing threading issues? In the debugger, it will show you there's a drop-down that you can see all of the, you can set a breakpoint that pauses all your threads. You can see a list of all the threads in the debugger. You can pick a thread and see the stack trace, like what code is running right now on that thread. So here's an example. The top one's the main thread. And the bottom one's the instrumentation thread, which is running the test case. And the top one is actually just waiting for the next message to come up on the main thread. So you can see it's in that activity thread main method, which calls loop, kind of the code that we saw at the beginning on the main thread. And the instrumentation thread is actually running your test. Another way to understand what's going on in a thread is the method tracing tool inside of Android Studio. It's a little bit hard to see, but if you can see up in the corner there, it says thread equals main. And you can see, maybe you can't see, basically there's two messages being processed here. So the red line there that you see at across there, that is, it's waiting for next. It's waiting for MessageQueue.next. And then the two kind of big blobs there are at the top of the call stack there is dispatch message. So this is the main queue. It ran one message, which had all these subcalls to other methods. And then it was done, and then it did, if you see the red line there, that's another next getting the next message. And then another kind of the raining down of the yellow there is the next message being processed, and all the methods that it called and the methods that those called. So when you're trying to understand there's something blocking the main thread, what's taking up all this time, this can really help you understand what messages are getting processed, how much time they're taking, what order they're going in, and things like that. So I want to touch on a few other things. These are just a little bit more grab bag topics that are related to the main thread. But when you call things on your activity, those go from the main thread outside of your process through the binder mechanism to an activity manager, and then come back for your method-like cycles later. So you call start activity. Activity manager does its thing. If it happens to be starting an activity that's also in your process, then it will come back. Sometimes you start activities that aren't in your process. So it's something to be aware of, that it's very asynchronous, that you put it on the main thread, it goes outside of your process, and eventually it comes back and you get the callbacks of onCreate, onDestroy, back on your main thread. This is one that's more a piece of trivia, I guess. I haven't had to use this knowledge too much, but there's a thing in MessageQueues called sync barriers, and it's really kind of an implementation detail. But certain things, like when the view is updating itself and things like that, they'll put a sync barrier on the main queue. And what that does is any message that's marked as synchronous will not get to the front of the queue until the sync barrier you can call remove sync barrier, and then all those synchronous ones. But there's a method, and we saw it in the code earlier with Choreographer. It said set asynchronous equals true. And that means that asynchronous messages can always get to the front of the queue. So that means even if your view is doing something and setting a sync barrier to block other messages from getting processed, that Choreographer is still going to draw that frame every 16 milliseconds because it's setting an asynchronous message that can get around that sync barrier that's set on the main queue. IdleHandlers. So I talked about earlier that MessageQueue doesn't have much on its public API, but the one thing you can do is set an IdleHandler. And essentially what an IdleHandler does is it gets on the main queue, but a way to think about it is that it's always putting itself at the back of the line. If anything gets in line to be processed, it goes to the back, and it goes to the back, and it goes to the back. So it only gets to the front when nobody else got in line to be processed. So it may never run because people keep getting in line. It's always going to be at the back. So you should never put anything in an IdleHandler that you like, this is important. If it doesn't run, things aren't going to work. If you really need to know like when the main thread has been drained and there's nothing at this very moment to be processed, that's what an IdleHandler is for. But just be aware that your IdleHandler callback, which is it tells you the queue is idle, that may never happen. Specifically if you have animations. Like if you have a progress spinner, every time that thing gets updated, the choreographer has to draw a frame. So it's basically keeping the main thread queue, the main message queue full by drawing animations. So if you have an IdleHandler, it's always going to the back of the message queue, and your IdleHandler may not get called. So when understood and used right, it can be a useful thing, but you just have to be kind of understand what exactly you're getting with that. All right, so here's a few things that I used. These are a journey on the Android main thread or some great blog posts that you should look at for some more information. And I think that brings us to the end of the talk. So I think we may be, we're almost at up time. I have like 2 minutes. So I will be at the Amex table, ready to talk about any questions. There's plenty of, we have our other Android engineers, we have designers here. And of course, like everybody, we're always hiring Android engineers and other engineers. So stop by and talk to us.